Welcome to the Chapter 8 Study Guide. I'm assuming you've already read through this problem since you have a handout with the problem in front of you. I'm just going to pull out the first two important words that I need and get rid of the rest of those words. So the first thing I like to do is go ahead and write down the individual ions because that helps solve the problem all the way through. So I know calcium is a 2+ charge and nitrate, sorry about that, lithium, and then carbonate. Now I'm ready to write the first two reactants. So calcium nitrate and lithium carbonate. Oops, need a 2. And when we do a double displacement reaction, then we know that things are going to swap. So for a double displacement reaction, we're just going to swap the anions. So we end up with calcium carbonate and lithium nitrate. Looking at your solubility rules, well, we know this one is your solid, this one's aqueous. We were told in the beginning that this one's aqueous, as was this one. Now we just need to balance it. Let's see, so we're definitely going to need 2 lithiums. I've lost my pen. All right, let me pause, see if I can get my pen to work. It's amazing how well things work when they're charged up. Okay, so there's the balanced equation. 2 lithiums, good, 2, we're all good. Now we just need to write the net ionic. Remember, that shows things as they exactly are in the solutions. Oops, plus a nitrate, plus 2 lithiums, plus a carbonate. And we're going to leave the calcium carbonate alone because it exists as a solid in the solution. Don't forget that we also have 2 nitrates. It's a common one students will forget. They'll forget to distribute that to both of those. The final thing we need to do now is just write the net. The net ionic equation shows only those species that play chemistry games. It's helpful to kind of circle it. So there's what was made and the 2 things that went into making it. Make sure you always start with the cation. So we have calcium plus carbonate, and that's going to give us calcium carbonate. Solid. This problem is very similar to the first one, but instead of having a precipitate made, take a look. What is it that we're going to make when we mix a strong acid with a strong base? Well, I like to get rid of all the words and just look at the important stuff. So here we go. We're going to take sulfuric acid. It's one of the ones that you should know. Whoa, look at that. Pen, crazy pen. We're going to erase all that. Erase, there we go. So here we have sulfuric acid, which is H2SO4. That is one of the ones you should know. Plus sodium hydroxide. Oh, that's a mess up. Got a little carried away there. All right, trying sodium hydroxide again. And now we're going to swap the anions. I like to rate HOH. That is water, but it does make the balancing a little easier to write HOH. Plus sodium sulfate. So now we need to balance this guy. Good deal. This is your product. It's a liquid. And then we have aqueous. There's our complete molecular equation. And now for the complete ionic equation, we're going to break everything apart and show how it exists in the solution. Don't forget that 2 distributes. And the water stays together. That's your product. The final step then is to write the net ionic equation. And so this is what was made. What 2 things went into it? Well, there's this one and this one. Now you can't just leave it like that, because there's one more thing that you need to remember to do, and that's reduce it. All these 2's are reducible. Good news, this is the net ionic equation for all reactions involving a strong acid and a strong base. Taking a look at this equation, you have to analyze that when the anions swip, that's hilarious. Okay, we'll try this again. You have to analyze that when the anions switch, do they make a precipitate? So when potassium hooks up with sulfate, does a precipitate form? When sodium then hooks up with nitrate, does a precipitate form? And the answer to this is no. You cannot write a net ionic equation because all of the ions are soluble when mixed together. And there's the molecular equation, and you'll notice that both potassium sulfate and sodium nitrate are soluble. So a commercial advertised their product, which contains carbonic acid, being super strong. Well, what's wrong with this statement is the word strong. Strong means the acid dissolves nearly 100%, and I gave you a list of strong acids. Strong means like this: hydrochloric acid dissolves to make hydrogen ions and chlorine ions when you put it in water. Carbonic acid is not a strong acid, it's a weak acid. So when it dissolves, yes, some of it goes to the hydrogen ions and the carbonate ions, but some of it stays as hydrogen carbonate or carbonic acid. So what the advertiser should have said was that the acid was super concentrated, meaning that there's a lot of acid relative to the amount of water. What you need to do for this problem, and I know the directions weren't terribly clear on your handout, but first off you need to balance it. Notice please that there is hydroxide on the reactant side. Is there a hydroxide available on the product side? Well, actually there is. It's sort of hidden in the water. So I like to rewrite the water when I notice that as HOH. It makes it easier to balance. So to balance this equation, you're going to need a 2 there because we have 2 hydroxides on the reactant side. And the second thing you need to know is to be able to tell me that this is an acid-base reaction. Also, an acid-base reaction is a double displacement reaction. If you can do all 3 things on this problem, you're good to go. This problem, for some unknown reason, was balanced on your study guide, but you do need to balance it. So if you'll notice that on the reactant side, you have glucose. For this type of reaction, you always want to balance the carbons first. So here we have 6 carbons, so we need 6. Now we're going to balance the hydrogens. We have 12 hydrogens here, so to give us 12, we need another 6. On the product side then, we have 6 times 2, which makes 12 oxygens, plus 6 times 1, 6, so we have 18 oxygens over here. We already have 6 oxygens here, so plus, we don't know what that is, so plus 2 times that number has to equal 18. So 2x is equal to 12. That means the coefficient in front of the oxygen needs to be a 6. The other thing you need to be able to do is tell me that this is a combustion reaction. And then you have bonus points if you also know that this is an oxidation reduction reaction. Or if that's too much of a pain in the butt to write, you can go ahead and write redox. But this, of course, would have been worth extra since I did not yet cover that in class. I know this problem is not on your study guide, but it should not come as a surprise to you that you have a problem on your study guide that is similar to the lab. So you need to describe to me how you would differentiate these 6 solutions. And while these aren't the exact 6 you would have, it is very similar in structure and design. So the first thing you would do is a conductivity test. This would allow us to identify the sugar water as it is the only solution that does not contain ions. So it won't light up the conductivity meter. The second test you could do is the acid-base test. That would allow us to identify both the sulfuric acid and the sodium hydroxide. Now, if you use a universal indicator, the sodium hydroxide will end up red, and I said that wrong. The sulfuric acid will end up red, and the sodium hydroxide ends up purple. Once you've identified the sodium hydroxide, take a look at that anion, the hydroxide ion. Will that form a precipitate with anything else in your list? Well, actually it will. It will make a precipitate with both the silver and the copper ions according to the net ionic equations listed there. Unfortunately, that won't tell you which is silver and which is copper. However, it will allow you to find the third solution that's left. Because the sodium chloride isn't going to make a precipitate with sodium hydroxide, you now know who the sodium chloride ion is. And I think on the last slide I said sodium chloride ion instead of solution. Sorry about that. Okay, now that you know the sodium chloride solution, those chloride ions are going to do something to help you figure out who is silver and who is copper. Well, if you mix the sodium chloride, you can tell the difference because silver chloride makes a precipitate, but copper chloride does not. Now you found the silver nitrate, which means the remaining solution is copper nitrate. Good luck on the test.